Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. The mapping problem, building the dictionary between language and world. We now continue our profound journey through Ep.8, the pure abstract language of the Holophase audio series, moving to part 34, the mapping problem. In the last part, we stood at the threshold between the perfect cathedral of abstract language and the noisy marketplace of physical reality. We built the conceptual bridge. We understood that implementation means taking our flawless phi patterns and trying to write them into the imperfect, noisy, limited book of the physical world. We saw how measurement introduces observers, instruments, and the possibility of error. We saw that the language of phi is like a perfect musical score, while physics is the real orchestra playing it with real instruments in a real hall. Today, we take our first actual steps onto that bridge. Today, we face the mapping problem. This is not a side note or a technical curiosity. This is one of the most important and practical tasks in our whole journey from pure language to physics. If we fail here, Holophase remains a beautiful story that never quite touches the world we live in. If we succeed, we begin to see every measured quantity in physics as a sentence written in the language of phi. The mapping problem asks a very simple but very deep question. How do we go from the abstract symbols of phi, from its values and derivatives, to the measurable quantities of our physical world? How does the symbol omega become a frequency we can count with a clock? How does k become a wavelength we can measure with a ruler? How does a topological winding number become an electric charge we can detect with an instrument? In other words, how do we build a dictionary between the eternal language of phi and the particular dialect of our universe? 1. The story core. Building the universal dictionary. Imagine you have discovered an ancient, perfectly logical language carved into the walls of a cave. You have spent years working out the alphabet. You know how the letters combine. You understand the grammar. You can read every sentence out loud. The language is phi. But there is a problem. Although you can read the sentences, you do not yet know what they are about. The language talks about omega and k and gradients and topological charges. It describes curves and twists and loops with perfect precision, but you do not yet know how any of this connects to birds, rivers, magnets, or stars. Then you walk out of the cave into the sunlight. You hear a bird sing. You feel the wind on your face. You watch a river flowing. You pick up a magnet and feel the pull on a piece of iron. You know, deep down, that this ancient language is supposed to describe all of this, but you do not yet know how. The mapping problem is exactly this task. You need to create dictionary entries that say things like, in the phi language, this symbol at this place corresponds to that physical quantity in the world. You want entries like, this omega pattern is the pitch of that bird's song, or this spatial gradient is the steepness of this hill, or this integer topological winding number is the electric charge at the end of this wire. On one side of each dictionary entry, you have a pattern in phi, a value, a derivative, a curvature, a winding, a holonomy. On the other side, you have a measurable quantity, a frequency in hertz, a length in meters, a charge in coulombs, an energy in joules. This is what scientists have been doing for centuries, often without saying it this way. Every time somebody wrote down a physical law, they were building a small piece of this dictionary. Newton, when he wrote force equals mass times acceleration, was saying, this combination of motion patterns corresponds to a push or pull you can feel and measure. Maxwell, when he wrote his equations, was saying, this combination of changes in electric and magnetic fields corresponds to light and radio waves you can detect. In the Holophase program, we are doing the same thing, but from a more fundamental starting point. We are building a dictionary that maps everything back to a single substance, phi, and its derivatives. Linguistic role, the dictionary between two worlds. In the language metaphor, the mapping is the dictionary that connects two tongues. The source language is phi and its structures. The target language is the language of physics: frequency, wavelength, speed, force, field, charge, mass, energy, temperature, pressure, and so on. The mapping rules are the dictionary entries. They tell us what physical quantity we should see when a certain pattern appears in phi. They also tell us what pattern in phi must exist if we see a certain measured quantity in the lab. But this is not a simple one-word to one-word dictionary. A single physical quantity often comes from a combination of phi structures, and a single phi symbol often contributes to many different physical quantities. For example, what we call kinetic energy in physics is not just omega or just k. It is related to how intensely something is moving and how strongly phi is curved in space and time. It might involve combinations like omega squared and k squared together. The mapping is something like this intensity of time change and this intensity of spatial variation together correspond to a number we call kinetic energy. Likewise, what we call electric charge is not simply phi at a point. It may come from a winding pattern of phi's phase around the loop. In that case, the dictionary entry would say, this topological winding number corresponds to this amount of electric charge. So the mapping is not a list of simple labels. It is a web of relationships. It says, when this pattern appears in phi, and you look at it through your instruments, it shows up as that physical quantity. The same pattern might show up in different ways from different points of view. Scientific essence, the question of correspondence. The scientific heart of the mapping problem is this. Given a physical measurement, what combination of phi structures is responsible for it? Think of a very simple experiment. You hang a pendulum from the ceiling. You pull it to one side and let it go. You time how long it takes to swing back and forth. Suppose you find that one full swing takes 2 seconds. The frequency is half a swing per second. In the phi language, we already know about omega, the rate of change in time. Our first guess might be that the pendulum's frequency maps directly to omega. One dictionary entry would simply be frequency equals omega divided by 2 pi. But we also know that the pendulum's motion depends on the length of the string and the strength of gravity. These are spatial and dynamical things. So the real mapping might be more subtle. Omega itself might depend on a curvature in the spatial pattern of phi and on how phi changes with height. The frequency might be linked to a combination of second derivatives in space and time. So the mapping task is to find the right formula that builds the measured quantity from the underlying phi structures. When we get that formula right and test it, we have created a new dictionary entry. When we repeat this process many times, we slowly build a complete translation manual between language and world. Dimensional expression, mapping the 3 echoes. Every physical quantity we measure carries information about time, space, and motion. So every dictionary entry must, in some way, involve all 3 echoes of the Holophase language. When we map time echoes, we are dealing with things like periods, frequencies, lifetimes, and decay rates. These will involve omega, the first and higher time derivatives of phi. A clock's tick is a repeating omega pattern. The half-life of a radioactive sample is a pattern in how phi changes statistically over time in many copies of the same system. When we map space echoes, we are dealing with lengths, areas, volumes, shapes, gradients, and curvatures. These will involve k, the spatial derivatives of phi. The wavelength of light is a pattern in k. The curvature of spacetime, in a field theory sense, is a large-scale pattern in how k changes from place to place. When we map motion echoes, we are dealing with velocities, accelerations, flows, and momenta. These require linking time and space derivatives. Motion is about how something moves through space over time, so it naturally combines omega and k. The speed of a wave is a simple ratio between the time change and the spatial change of phi. A flow in a fluid is a vector field built from how phi patterns move in both space and time. The key point is that no physical quantity is purely one-dimensional. When we measure a frequency, we measure how often something moves in time while it sits in space. When we measure a distance, we send light that takes time to travel. When we measure speed, we measure how much space is covered in a certain time. The mapping rules in our dictionary will naturally mix Phi's time, space, and motion structures, because reality itself always mixes them. V. Position in the master tree, the interface layer. Inside the master tree of the Holophase language, we have already grown many branches. We have branches for derivatives, branches for topology, branches for holonomy, branches for quadratic forms, branches for wave patterns and resonance. The mapping layer is not another branch that goes further into abstraction. Instead, it is like the layer of leaves at the edge of the tree, where the internal sap meets the external world. Each mapping rule is like a leaf. On one side, the leaf is connected to the branch of abstract structure. On the other side, it faces the air and sunlight, where it exchanges gases and light. In our metaphor, that outer side of the leaf connects to physical measurement, experiment, and experience. One leaf might be the rule. Topological winding number maps to electric charge. Another might be particular combinations of omega and k map to mass energy. Another might read phase holonomy around the loop maps to a measurable quantum phase shift. For the tree to be healthy, every leaf must be both mathematically consistent with the branch it grows from and empirically consistent with the world it touches. If the mapping rules were inconsistent with Phi's grammar, our theory would collapse internally. If they were inconsistent with experiment, our theory would fail externally. So this interface layer is where our abstract language proves its value or reveals its limits. Relations to neighbors, using all our tools. To build a mapping dictionary, we must use all the abstract tools we developed in earlier parts. From basic derivatives, we use omega, k, and v to represent changes in time, changes in space, and patterns of motion. These give us the first entries for frequencies, wavelengths, and velocities. From quadratic forms, we build expressions like omega squared and k squared that are always positive and measure intensity. These help us map to physical quantities like energy density, pressure, and intensity of radiation. Energy in this picture is not a separate substance. It is a way of counting how strongly Phi is patterned. Our mapping rules turn those abstract counts into the energies we measure in experiments. From topology, we use knots, defects, and winding numbers. These are global patterns in Phi that cannot be smoothed away. They give us natural candidates for explaining why certain physical quantities come in discrete units. A winding number must be an integer. If charge is mapped to such a winding, charge is automatically quantized. From holonomy, we use path-dependent phase accumulation. These abstract structures map to physical effects where a system remembers the history of its motion, such as in the Aharonov-Bohm effect. The mapping says, this abstract holonomy equals this observable phase shift in an interference pattern. From spectral modes, we use standing waves and resonances in Phi to represent stable patterns. These map naturally to elementary particles, which behave like standing patterns of vibration in the underlying field. In this way, the mapping problem is not an isolated step. It draws threads from every branch of the master tree and ties them into knots that we can test in physics. Semantic meaning, naming what we measure. At a deeper level, mapping gives semantic meaning to the holophase language. Without mapping, Phi symbols are like sounds with no agreed meanings. With mapping, they become words that name the patterns we experience. When we map a certain combination of derivatives to temperature, we are saying this pattern in Phi is what we are really sensing when we say something is hot or cold. When we map a winding number to charge, we are saying this twist in Phi is what our electrometers respond to. When we map a wave equation to light, we are saying this special family of Phi patterns is what our eyes and antennas detect. So mapping does three kinds of work. It grounds the language in reality, it assigns quantities to patterns, and it turns the phi language into a predictive tool. Once we know that a certain pattern is mapped to a measurable quantity, we can predict new situations where that pattern will appear, and therefore new measurements we should see. Stability and falsifiability, when dictionary entries break. Because mapping links language and world, it is also where our framework can be most sharply tested. If a proposed mapping rule consistently fails, despite careful adjustment and honest effort, that failure is not an embarrassment. It is information. It tells us something important about the relation between phi and the world. For example, suppose we try to map a known physical quantity, like the electric charge of all the known particles, using topological winding numbers in a single phi field. We build a rule that says charge equals a constant times the winding number. It works for electrons and protons, but fails for some other particle. No matter how we adjust the details, we cannot get all the measured charges to fit. That failure could mean several things. It might mean we need more than one phi field. It might mean the mapping rule is more complex, involving holonomy as well as winding. Or it might mean that our assumption that charge is purely topological is wrong. If, after exhausting all reasonable mapping strategies within the Holophase framework, we still cannot reproduce the pattern of observed charges, then the mapping problem becomes a falsification problem. Either our version of Holophase is missing an essential ingredient, or the entire idea that one field can encode all charges could be wrong. The same logic applies to any quantity. If there is some measured property in physics that resists all attempts to express it as a combination of phi structures, then that property is a candidate witness against the universality of the phi language. This is how we keep ourselves honest. The dictionary is not invented freely. It is constrained both by the internal grammar of phi and by the external facts of the world. 9. Examples across scales. Seeing the dictionary at work. To make this truly vivid, let us walk through a few more examples, from the very small to the very large. Think of the pitch of a note on a guitar. Physically, we measure it as a frequency in hertz. In terms of phi, the vibration of the string is a time-dependent and space-dependent pattern. Somewhere in that pattern, there is a dominant time derivative, an omega, that repeats regularly. Our mapping rule tells us how to take that omega value and turn it into the frequency number we record. Once we understand that mapping, we can predict how changing the string's length, tension, or density will change the pitch. Think of the charge on an electron. We measure it as about negative 1.6 times 10 to the minus 19 coulombs. In the phi language, the electron is a localized, stable pattern, perhaps a topological defect in a field. The mapping rule might say that if you go in a loop around that defect and watch how phi's phase changes, you will see it wind once in a particular direction. That single winding, multiplied by a fundamental constant, gives you exactly the electron's charge. Nothing mystical, just a twist in the underlying field. Think of the speed of light in vacuum. We measure it as a fixed number, about 300,000 kilometers per second. In phi terms, light is a wave solution of the field equations. The mapping rule says that in vacuum, for that solution, the ratio between the second time derivative and the second spatial derivative of phi is fixed. That ratio is c squared. Measured speed becomes a structural property of the field's differential relations. Think of the temperature of the air in your room. We measure it with a thermometer. In phi language, the air is a huge collection of small excitations, each moving with some velocity. The mapping rule says that the temperature is proportional to the average of the squared motion intensity over all those excitations. Hotter air means larger average v squared, and therefore a higher intensity in the motion echo of phi. Once you see these examples, you can begin to imagine mapping rules for more complex things. Pressure in a star, viscosity of a fluid, refractive index of glass, even effective quantities in biology like nerve conduction speed or membrane potential. Recognition skill, seeing mappings in daily life. You can practice this way of seeing the world right now. Whenever you hear a physical quantity mentioned, imagine there is a small dictionary entry next to it that points back to phi. When you hear frequency, imagine omega. When you hear gradient, imagine spatial derivatives. When you hear energy, imagine intensity of patterning. When you hear charge, imagine twists and windings. Look at a simple electrical circuit: a battery, a wire, and a light bulb. The battery's voltage is a mapped quantity. It relates to how phi is arranged across the terminals. The current in the wire is a mapped quantity. It relates to how charge defects or excitations move through the field. The bulb's brightness is a mapped quantity. It relates to how much phi patterning is being converted into light wave patterns per unit time. Look at the sky at night. The color of a star is a mapped peak in the spectrum of its light, which maps back to patterns of thermal agitation in the star's plasma, which map further back to distributions of phi excitations in the star's core. Return to phi. One field, many names. At the end of this part, we return again to the simplest statement. There is one field, phi, and its derivatives. That is all. The mapping problem does not introduce new substances. It explains how the single substance presents itself to us under many different names and numbers. When we say phi maps to frequency, phi maps to charge, phi maps to energy, we are not multiplying the ontology. We are describing different stable and measurable aspects of one underlying pattern. The numbers we write down in our notebooks are just the human way of tracking those aspects. As we go forward, we will keep building and refining this dictionary. We will propose concrete mapping rules for specific parts of physics, for classical mechanics, for electromagnetism, for quantum theory, for thermodynamics. Each new rule will be a test of the language we have built, and a new window into the way the world actually works. Zooming out, remember the full picture. There is one field, phi, whose differentiation gives rise to time, space, and motion together. Every higher derivative is a finer question about how phi changes, and each question casts three shadows: temporal, spatial, and kinematic. These echoes weave together into the entire tapestry of existence. In Episode 7, we climbed the master tree of this language. In the early parts of Episode 8, we built its pure abstract cathedral. In the last parts, we proved its consistency, its breadth, and its limits. Here, in Part 34, we are building the dictionary that links that language to the concrete world. You are learning not just to hear the story of phi, but to translate it into the numbers and concepts that physics uses. You are learning to see that every equation, every measurement, every pattern in nature is, at its core, a sentence in a single, universal tongue. Human analogies, making the mapping intuitive. It can help to look at the mapping problem through simple, human analogies. First, think of translating poetry from one language into another. In the original language, a single word can carry layers of meaning, emotion, and rhythm that have no exact match in the target language. You cannot always replace one word with one other word. Often you need a whole phrase or a careful choice that depends on context. Translation is an art of matching patterns of meaning, not just swapping symbols. The same is true here. A single structure in phi may need several physical concepts to describe it fully. A single physical quantity may arise from several different pieces of the phi pattern. Our dictionary between phi and physics is not a simple one-to-one table. It is a careful, evolving art of matching patterns in one description with patterns in another. Second, think of a map and the land it represents. On the paper, you only have colored lines and shapes. A thick line might stand for a motorway. A dashed line might stand for a footpath. Blue areas might mean lakes and rivers. Green patches might mean forests. None of these things are literally sitting on the paper. They are meanings attached to patterns of ink. To use the map, you must know the legend that tells you how to interpret those patterns. In this analogy, phi is like the land itself, the real terrain. The mapping rules are like the legend of the map. They tell us that this kind of twist in phi corresponds to that kind of field in physics, or that kind of oscillation in phi corresponds to that kind of measurable frequency. Physics, as an experimental science, is then the ongoing test of whether following this legend actually guides us to the right places in the world. Third, Think of written music. The same sequence of notes on a page can be played on a violin, a piano, or a flute. The abstract notes and rhythms are like patterns in phi. The particular instrument is like a particular physical medium that implements those patterns, with its own limits, noise, and texture. The mapping rules tell us how the same abstract structure shows up as different concrete sounds, while still being recognizably the same melody. All of these pictures share one simple idea. There is one underlying structure that can appear in many guises. The mapping rules connect the underlying structure to each particular appearance. In our story, the underlying structure is always phi and its derivatives, and the particular appearances are the many measurable quantities and phenomena that make up our universe. Preparing for the concrete journey, from dictionary to dynamics. By now, you can feel that the mapping problem is not a side puzzle. It is the doorway through which the Holophase language must pass if it is to become a concrete physical theory that can be tested and refined. In the background, we keep the pure abstract picture. One field phi, its first derivatives giving time, space, and motion, its higher derivatives forming infinite structures. In the foreground, we now begin to ask new kinds of questions. When we say in everyday physics that a particle moves at constant speed in a straight line, what does that really mean in phi symbols? When we say that a force acts and changes motion, what combination of derivatives and patterns are we pointing at? When we say that a wave carries energy from one place to another, what exactly is happening in the holophase field? Each of these questions has two sides. The mapping side asks, which physical quantity are we naming here, and how does it sit in the dictionary? The dynamical side asks, how does that quantity evolve, and which equations for phi generate that evolution? Every time you look at a law of physics and wonder, what is the underlying phi pattern here? You are walking further across the bridge between language and world. Every time you see a number on an instrument and imagine the hidden field structure behind it, you are becoming more fluent in this universal tongue. Peace be upon you.